Thank you, Luca and Ariel, for this nice invitation to speak in this wonderful workshop, and thank you everyone for attending. So I will be telling you about Axion's relics produced in non-standard cosmologies. This is some work that we've been developing together with some colleagues that are shown here. And it's based on these two papers that are here. So first I will motivate you briefly about why to consider these non-standard cosmologies before the onset of BBN. Then I will talk about production of cold dark matter axions, and some remarks about that we highlight in this work. Then I will move to thermal production, and then I will conclude. So our most accepted picture of the universe is that first the universe went through a period of inflation that could have happened at energy scales as high as 10 to the 16 GeV. But on the other hand, we have evidence that at the moment of Big Bang nucleosynthesis, the universe should be radiation dominated. So even though these two periods are separated in a really short fraction of time, the energy scale could be as high as almost 20 orders of magnitude between those two epochs. So it is not so crazy to think that might be that in between some other energy form took over the expansion of the universe and left some imprints in production of cold and hot relics. So some usual scenarios that are considered, is, for instance, low temperature reheating, or an early matter domination phase, kination, and these non-standard cosmologies have been well studied both in the case of Axion production in WIMP production. So I will be focusing this time on Axions. So, okay, I will not say anything about the misalignment because I know I can skip this figure. The only thing I want to stress is that in a radiation-dominated period, we can produce this plot here, which is the misalignment angle versus the axion mass, that in order to account for the two possible scenarios, which is an axion in the pre-inflationary era or post-inflationary era, we selected here these two values of this initial angle, and therefore we can talk about a window of axions produced by the misalignment mechanism that one would call natural, right? So this is what I will be referring to as a cold dark matter window in standard cosmology, this mass range here. Yeah, so now I will introduce how do we parameterize these non-standard cosmologies. So we assume, as I said, that before the onset of Big Bang nucleosynthesis, some other field or fluid with some equation of state and therefore a state parameter took over the expansion of the energy density of the universe, such that it follows this dynamical equation, and eventually it decays before BBN if the equation of state is smaller than the radiation equation of state, or it will naturally decay in the case of stiff fluids or stiff-like fluids. And we assume that this energy or this entropy release goes into the radiation bath. And in the case of the misalignment production, it's not shared by axions. This is a typical plot of the energy density of this new field in terms of the scale factor. And in here, I mark 3 stages. This first and second stage are the adiabatic periods, where still no energy has been released to the bath. And we parameterize this non-standard cosmology with 3 parameters: the equation of state, this equilibrium temperature, Tx, that marks the moment where the energy density of radiation equals the energy density of this new field, and then this end temperature, or Tend, that marks the moment where this new field decays, and then radiation takes over again. We also, in the misalignment production, we only considered early matter domination and some other cosmologies, but no low temperature reheating. But the extrapolation to low temperature reheating is direct. And in the thermal scenario, we did consider low temperature reheating. Yeah, so there are 2 effects that are important for the relic abundance if the oscillation temperature of the axion is higher than this Tn temperature. So in here you can see the Hubble parameter in the case of a radiation dominated scenario. This is the grain line. And the dashed blue line is the evolution of the Hubble parameter in terms of the temperature for a non-standard cosmology. And you can see that when you look for the crossing with the axion mass, that is temperature dependent, that this crossing happens at smaller temperatures. And therefore, this has the impact to increase the energy density of the relic axions. So this is the first consequence. And the second, in the case of cosmologies with omega, the equation of state smaller than 1/3, is that the axion energy gets diluted because of this entropy that is not shared by axions. So this is quantified here by this for this gamma parameter. In the case we don't have entropy injection, which would be the case for omega higher than 1/3. The only effect of this non-standard cosmology is this smaller oscillation temperature that then would lead to an increase in the energy density. Yeah, so about the entropy dilution, I will really quickly show you how it looks like for these different regimes, these 2 adiabatic regimes. Is given by this expression. So the ratio of the 2 temperatures that mark the beginning, let's say, and the end of the dominance of this new field. These are for some benchmark omegas that we considered. So of course, as the longer the non-standard cosmology is, the highest the dilution for the axion energy density. And for when the oscillation happens in this stage 3, where the field already starts to decay, this is the entropy injection. Now this ratio is smaller. And this is how it looks like for these benchmark values. For low temperature reheating, there's only stage 3. So the oscillation happens during the non-adiabatic phase. So what we did is that we studied cosmologies, different cosmologies, And we look in which parameter space they could lead to the full explanation of the dark matter paradigm. And when analytically and numerically, we found the mass ranges that can account for the oscillation to happen in these different stages of the dominance of the new field. So we check cosmologies with entropy dilution, which would be omega equals 0 and omega equal to -1/3. And without entropy dilution, so omega equal 1, which is known as kination, and omega equal to 5 divided by 3. So this is our result. So let me explain you first this plot. This is this equality temperature versus the Axion mass. And we fixed the end temperature, this T end, we fixed to the smallest possible value, which is 4 mega electron volts, so before Big Bang nucleosynthesis. And here I remind you that this is what we call the standard window for the Axion cold dark matter. And this is how it looks when you introduce now a non-standard cosmology. In this case, we took early matter domination, I think in here, yeah. So if the oscillation happens in what I call this stage 1, which is the oscillation temperature higher than this equilibrium temperature, you can accommodate the dark matter, the total dark matter abundance in this whole range of masses and Tx. We saw that only oscillation temperatures that are higher than the QCD temperature are possible to reproduce the abundance, the correct abundance. In the case that the oscillation happens in this stage 2, so the oscillation temperature between the dominance of the new field, but before it starts to decay, this is how it opens up, let's say, the mass range. In here, you can either have that the oscillation happens after or before the QCD phase transition. And finally, in stage 3, where the oscillation temperature happens during this non-adiabatic phase, this is the mass doesn't depend anymore on this equilibrium temperature and therefore goes straight in here. This is the same plot basically for a different cosmology for omega equal to -1/3, where we actually can go to a bit smaller masses than in early matter domination. And this is the same for this stiff-like cosmologies. So kination is the red band, and this omega equal to 5 divided by 3 is this bluish band. And now you can see that we move to the other side of this standard window, because as I said before, the only consequence of these non-standard cosmologies is to increase the energy density for a given mass. So in order to accommodate the whole dark matter abundance, the mass moves to the other side of the window. So this is how it looks like, the open up of this parameter space where Axion can explain the whole dark matter abundance for different cosmologies. And this, of course, is an opportunity to test this kind of scenarios in these experiments, both in the high mass range and in the small mass range. Okay, so now I will be telling you about the consequences for the thermal production. So we know that in principle, if this interaction term between axions and gluons is operative during, let's say, radiation domination, we kind of know that unavoidably we end up with some thermal population of axions that actually could even be in tension with some astrophysical observations. So we looked into these KS-visit-like scenarios where there are new heavy quarks that carry Peccei-Quinn charges, and to proceed with our work, we took advantage of improvements in the computing of the interaction rate of for axion. Advances that have moved forward in this energy scale. But in order, to look into axion production, we took into account this smooth rate that goes from small to high energies. So in non-standard scenarios, non-standard cosmologies, the thermalization of axions can look really different. So this is a plot precisely of that. So in here I have the scale FA and this Tn temperature, and the lines are different cosmologies. So you see here standard cosmology, low temperature reheating, early matter domination, kination, and omega. For completeness, I included this. I will show you later why. So if you assume that the mass of this heavy fermion is around 10 to the 5 GeV, the axion in a radiation-dominated period thermalizes for Fa smaller than this number, fully thermalizes. But it's not the case in, for instance, low-temperature reheating. Well, I haven't explained, sorry. Everything below the curves is in thermal equilibrium for the given parameters Fa and Tn. Oops, sorry. So for instance, for low temperature reheating, depending on the end temperature, the thermalization of the axion can be really delayed to higher masses. The same for this cosmology here. And this has to do with the different scales in temperature of the interaction rate and the Hubble parameter, since we are comparing the two in order to establish whether the population thermalizes or not. Again, in this cosmology, in these non-standard cosmology scenarios, the axion decouples earlier than in a radiation-dominated scenario. And the energy density gets diluted if this decoupling temperature is above this Tn temperature, and this has consequences for the effective number of neutrinos, overabundance, and impact on large-scale structure. So these are how the observables, let's say, the contribution to the effective number of neutrinos, the contribution to the energy density, and the contribution or the average velocity of the axion, which translates into this free streaming length of the axion, change or get modified because of the non-standard cosmology. These are again these entropy dilutions depending on where this decoupling temperature is located in this non-standard period. What I would like to stress is that the most, let's say, affected quantities by the dilution are the effective number, the contribution to the effective number of neutrinos and the relic abundance, and not so much the velocity, which goes with the entropy dilution to the 1/3, and this other to the 4/3, and to the 1. Even though this, I'm sorry, I forgot I had this plot. This is to show you how dramatically can change the free streaming length. in these non-standard cosmologies. So in here, I have different cosmologies. These are all early matter dominated. This is the standard cosmology. And you can see that, for instance, if you have a Tn of 10 to the minus 1 GeV, a mass of 10 to the minus 2 can have more or less the same free streaming length as an axion of a couple of few electron volts. So the impact can be quite severe. But I wanted to stress that even though these parameters look that they are differently affected, they are related. They are not all independent. They are related by this relationship here, and therefore one shouldn't expect that in this case the velocity of the axion could impact so much if, for instance, the relic abundance is really suppressed. So what we did to get constraints was to consider the work or the results of this paper here, that they look for constraints on light but massive relics of any kind, fermion or boson-like. And they produced data using different observations. They used, okay, I didn't write, I'm sorry. Well, they used Planck, baryon acoustic oscillations. They used large-scale structure data and so on. And this is what we found was the most up-to-date data that we could use to constrain this model. So we translated their results into this plot. And here the red line is the QCD thermal axion population in a radiation-dominated scenario. So everything below the blue curve is allowed. Is allowed parameter space, and everything in white, therefore, is ruled out. And the black line is a thermal population in early matter-dominated phase with some entropy dilution that I tuned to 0.24 just to show the comparison between the two. So using this data, we produce this plot, which is the mass of the axion in terms of this Tn temperature for low temperature reheating scenario. So everything in the red region is excluded by this 95% confidence level. Here we mark some important, okay, thank you. We mark some important the temperatures where the decoupling temperature is equal to the QCD temperature, or the decoupling temperature is equal to the Tn. And so actually this one is interesting because everything to the right of this curve, all the decoupling of the axion to the right of this curve happens, during the standard cosmology. So after the non-standard cosmology has ended. And only this small region here is parameter space that where actually the decoupling of the axion happens during the non-adiabatic phase. And we show in here for comparison the work of Pierluca Carenza and others that they also considered this kind of scenario. And we see that because we included this large-scale structure data, we managed to go to constrain this region that they didn't. This is the same plot for early matter-dominated cosmologies. Here the different lines, so for instance, the solid line corresponds to an early matter-dominated phase with a huge entropy dilution. Then the dotted lines correspond to early matter-dominated cosmology with not so heavy dilution, and then this dotted dash is the even less diluted, just to show how they they differentiate depending on the dilution to the relic abundance. Yeah. So we also looked into the coexistence between a cold dark matter population and a hot axion population. So we know in standard cosmology this coexistence can only happen between a really highly diluted, probably even subthermal population of hot axions, as this plot here demonstrates. This is the energy density versus FA. And then you can see the contribution to the thermal energy density and how it goes with the misalignment production. So, but this doesn't need to be the case for non-standard cosmologies, because I'm sorry, it's getting crazy. Yeah, because I showed you that in for the misalignment production, if you consider this stiff-like cosmologies, you can actually explain the axion dark matter in the higher, let's say, or higher mass range than this standard cosmology. And this is what we use to show that a coexistence would be possible between hot axions and this stiff-like cosmologies with a cold dark matter population. So really briefly, because I'm running out of time, what we did was to take the data from this paper, which actually they look for sterile neutrinos, light sterile neutrinos. So in this case, in order to make just an educated guess, we mimic an axion to a light non-thermal they used this, well, from 2008, so this is what they had available back then. And from this, we produce this plot, which is the end versus MA. This is the band where the axion explains the cold dark matter abundance from the misalignment mechanism in a cosmology with this parameter. And the lines here show the relic abundance of a thermal or subthermal population of hot axions. And for instance, in here, we could have coexistence of subthermal hot axions with a relic density of 10 to the minus 3 with the cold dark matter population in this whole range here. The red region is where this hot population is excluded by the data I showed you before. And everything above this solid line is where the axions thermalize. Okay, so these are my conclusions. I would like just to stress that would be really nice if we have a discovery in the near future, that we can use this discovery of either cold dark matter or hot dark matter to learn more about the early universe and the history of the universe. So this is more or less the spirit of these works. So yeah, thank you very much. And if you have any questions, I'm happy to answer.
Thank you, Paola, for the nice talk. Any question, David?
Yeah.
So maybe I have one. So when you show the relic axions, so how you can compare with the standard cosmology case? What will be the ratio between both cases?
Sorry,
I could not read very well the difference. So,
in which case are you asking? Sorry.
So on the standard cosmology case, sorry, for the non-standard cosmologies. So when you show the relic the relic axis, And yeah, I want to know.
You
I want to
mean,
read.
I keep going out of this. You mean the cold dark matter axions or the thermal axions?
Thermal, sorry, thermal.
So this plots, for instance, or the coexistence. I don't think I'm following what you mean.
You have a relic abundance, right? In the non-standard cosmology, with the thermal axion, right? And you also have this for the standard cosmology.
I mean, for the thermal axions, I in this kind of cosmology, in these lines show the abundance of let's say, in this case, subthermal axions, because they do not thermalize, they are below this line.
Mm-hmm.
And how could they coexist with a cold dark matter population that lives in this band? But I'm not sure.
I say no. I mean, in a standard cosmology, you have thermal axions, right?
Yeah.
Which are a few. It's very. You can have like an axion background, like a CMB, but of axions, but it's very. Yeah. So in the non-standard cosmology, you also have thermal relics, right?
Yeah.
Yeah. So I want to know how I want to read how is the difference between both cases.
Well, for instance, in this low temperature reheating scenario, so if you take this T end really, really high, you go to the standard cosmology. So you could say that the axion is ruled out, that the standard cosmology axion is ruled out around 0.2 electron volts for masses above that. But in a non-standard cosmology like low temperature reheating, you relax those constraints. When this Tn temperature is lower than, well, some around 100 mega electron volts, and but even though you relax and all this parameter space, for instance, now is open, so it's not constrained. For masses of electron volt, for instance, and Tn of around 50 mega electron volt is not constrained. But even though you can constrain the decoupling of these thermal axions during the non-standard cosmology using this large-scale structure data, and this is how they compare in that sense. I mean, you can really lose the bounds compared to the standard scenario, depending on the features of this new cosmology or this non-standard cosmology.